It's a huge question, isn't it?
Yeah. Are we, made of tiny solid bits? Or are we maybe just swirling energy?
That's basically the debate physics had for centuries, this sort of scientific tug of war.
Right, like particles versus waves. You had Newton thinking light was tiny balls.
Corpuscles, yeah. And
Yeah.
then Huygens saying, no, no, it's a wave.
Exactly. So today, we're doing a deep dive into this really compelling idea. What if all matter is just a wave? Like maybe the whole particle concept is just redundant.
It's a tempting idea, and there's a line of reasoning people often follow to get there.
We want to unpack that. We'll start with, the equation.
Game PCI inevitably.
Then move through some seriously weird experiments.
Oh, they get bizarre.
And land on what modern physics actually says. So our mission is, does everything as a wave really hold up? And if not, what is the deeper answer?
And we're drawing heavily from this fascinating report. From duality to fields, a unified conception. It really challenges everyday thinking.
Okay, let's jump in. That idea that everything is energy often kicks off with implying. It's probably the most famous equation ever.
Absolutely. Everyone knows it.
But is it really the smoking gun for saying, matter is fundamentally wave-like? Does it actually mean that?
Yeah, that's where the popular understanding often goes a bit astray. It's fascinating how it gets misinterpreted in this specific context.
How so?
Well, MCMA was absolutely revolutionary for understanding mass and energy, no doubt. But by itself, it doesn't directly imply that particles are waves.
So the jump from mass is energy to everything is a wave based on that equation is flawed.
It's a bit of a leap.
Yeah.
The equation specifically talks about an object's rest energy.
E0 of energy.
Yeah, the energy something has just by having mass, even if it's perfectly still. Think of it as this huge reservoir of potential energy locked inside mass.
Okay, like it's waiting to be converted.
Exactly. And we see that conversion. Nuclear reactions, fission, fusion. That tiny set of lost mass, the mass defect, it turns into a massive energy release, just like EMC predicts.
Right.
And it works the other way, too. Energy creating mass. Pair production is the classic example.
We're a photon.
A high-energy photon, pure energy, spontaneously becomes a particle and is antiparticle. Like an electron and a positron, bang, out of energy.
Wow. Okay, so it definitely blurs the lines between mass and energy. That must have fundamentally changed how we even define mass.
Right, completely. It was a profound shift. Classically, mass was just inertia, how stubborn something was about moving.
How much stuff it had.
Pretty much. But relativity says mass reflects the total energy content of a system. So get this. A hot iron block is actually infinitesimally heavier than a cold one.
Just because it's hot?
Because of the thermal energy, yeah.
Right.
A compressed spring is heavier than a relaxed one. Potential energy adds mass. Even the Earth spinning makes it slightly more massive.
That's wild. So it blurs those classical distinctions for sure. But if EC isn't the direct link to wave behavior, where does that idea actually come from?
Good question. Because the popular EMC potty is, well, it's a simplification.
There's more to it.
There is. The full relativistic equation is the energy-momentum relation. E squared equals PC squared plus M naught C squared squared. So EPC plus MAC.
Okay, but the more complex. What's the P there?
P is momentum. And this equation shows total energy has two parts. One from rest mass, the MEC bit, and one from momentum, the PC bit. They're distinct contributions.
Ah, so energy from just existing and energy from moving.
Exactly. And for things without mass, like photons, the rest mass term is zero, so it just becomes EPC. Energy equals momentum times the speed of light.
I see.
And here's the crucial point. The wave-like nature of matter. It's fundamentally tied to momentum, P, not the rest mass. The energy locked up in mass is separate from the momentum energy that dictates its wavelength.
Okay, my head's spinning a bit. Even Siva is about rest energy, but the wave stuff comes from momentum. So who figured that out, that link between momentum and waves for matter?
Right, that was an Einstein. The real breakthrough there came from Louis de Broglie in 1924.
De Broglie. Okay.
He had this truly revolutionary idea. He proposed that all matter, not just light, should have wave-like properties. Everything, electrons, protons, baseballs, you name it.
Everything. How did he quantify that?
With the de Broglie equation, lambda equals h over p EAAP. Wavelength, lambda equals Planck's constant h divided by momentum. That's the equation that assigns a wavelength to matter, not E is to lambda.
Lambda equals p. So wavelength depends on momentum. Was that just like a cool theory, or did they actually find evidence?
Oh, they found evidence, and pretty quickly, too. 1927, two physicists, Clinton Davison and Lester Germer.
What did they do?
They were firing electrons at a nickel crystal, and what they saw was a diffraction pattern.
Diffraction, like when waves bend around corners?
Exactly. The pattern was identical to what you'd get if you shone X-rays, which they knew were waves, through the crystal. It was undeniable proof that electrons, these things they thought were particles, were behaving like waves.
Wow. And has that been shown for other things too?
Absolutely. Neutrons, protons, even whole molecules, quite large ones actually, have been shown to exhibit this wave behavior. It's universal.
Okay, and nothing quite captures this weirdness, like the double-slit experiment, right? It's almost infamous.
It really is the icon of quantum mystery.
Could you walk us through it for anyone who hasn't encountered this mind bender yet?
Sure. So classically, imagine you've got, I don't know, a paintball gun. You fire a paintball through two narrow slits onto a wall behind. What do you expect?
Two strips of paint line up with the slits?
Right. Simple.
Mm-hmm.
Now, imagine sending water waves through two openings. What happens on the other side?
You get that interference pattern,
Yeah.
ripples crossing, canceling out in some places, adding up in others. Bright and dark bands, sort of.
Exactly. That's wave behavior. Now, the quantum version. Fire electrons, one by one, at a barrier with two slits. What do you see on the detector screen behind?
Okay, based on Davison-Germer, maybe an interference pattern?
You do eventually see an interference pattern, which is crazy. But here's the kicker. Each electron arrives as a single localized dot, like a particle hitting the screen.
Wait, so they hit like particles, but build up a pattern like waves?
Precisely. And it gets weirder. This happens even if you fire them so slowly that only one electron is going through the apparatus at any time.
One at a time. How can one electron interfere with anything?
It seems it has to interfere with itself.
Yeah.
Which means somehow that single electron must have gone through both slits simultaneously, like a wave spreading out.
That just breaks my brain. How?
Welcome to quantum mechanics. But wait, there's more.
Oh, great.
The truly bizarre twist is observation. What happens if you put detectors right at the slits to see which slit each electron actually goes through?
Okay, what happens? Do you see it go through one or the other?
You do. You find out which path it took. But the moment you get that which way information, poof, the interference pattern completely disappears. Gone. You just get two strips on the screen exactly like the paintballs.
Just by looking.
Essentially, yes.
Yeah.
The act of measuring which path forces the electron to behave like a classical particle. It suggests measurement isn't just passively watching. It's an active process that fundamentally changes the outcome. Gaining information destroys the wave-like superposition.
So matter can act like a wave, but then light, which started this whole wave thing, can also act like a particle, right? The photoelectric effect.
Exactly. That's the other side of the coin. Just as matter's wave nature was being confirmed, light's particle nature became impossible to ignore.
How did that work again?
The photoelectric effect is when light hits a metal surface and knocks electrons out. Classical wave theory couldn't explain it properly. It predicted that brighter light, more wave energy, should always knock out electrons eventually, maybe with more energy.
But that's not what happened.
No. Below a certain frequency of light, no electrons came out, no matter how bright the light was. But above that frequency, even dim light knocked them out instantly.
Weird.
Einstein explained it in 1905 by proposing that light energy isn't continuous, but comes in discrete packets, quanta. We call them photons.
Packets of light energy.
Yep, with energy, equal F, energy equals Planck's constant times frequency. A single photon needed enough energy, high enough frequency, to kick out one electron. Brighter light just meant more photons, not more energy per photon.
So one photon, one electron, like tiny billiard balls.
In a way, yeah. It cemented the particle nature of light, so you're left with this unavoidable paradox.
The duality paradox.
Right, things like electrons and photons sometimes act like waves, sometimes like particles, depending on how you interact with them. It's context dependent.
So what is the wave then, if it's not a physical ripple?
The modern understanding, thanks to Max Born, is that it's a probability wave. The wave function, size, doesn't describe a physical substance spreading out.
Okay, what does it describe?
It describes the possibilities. Its value at any point, or rather the square of its value, tells you the probability of finding the particle at that point if you were to measure it.
So it's like a cloud of likelihood.
That's a great way to put it. A fuzzy cloud of probabilities, the wave-like interference pattern we see. That's the statistical result of many particle-like detections distributed according to those probabilities.
Okay. But this leads to a huge problem, doesn't it? If an electron is just this cloud of probabilities before we look, how does it suddenly become a definite thing in a definite place when we look? What makes the cloud collapse into one spot?
You've hit the nail on the head. That is the infamous measurement problem. It's arguably the deepest mystery in quantum mechanics.
Tell me more. How does the theory describe this?
Well, the wave function, according to the Schrödinger equation, evolves smoothly, deterministically. It spreads out, contains all possibilities in superposition. But the moment a measurement happens, bang, this smooth evolution is violently interrupted. The system instantly jumps into one single definite state.
The wave function collapses.
Exactly. But standard quantum mechanics just postulates this collapse happens. It doesn't explain how or why this probabilistic description turns into a single reality upon measurement. That's the core issue.
So how do physicists deal with this? Do they just ignore it?
Not exactly. They've come up with different interpretations of quantum mechanics. These are ways to make sense of what the math means for reality, and they offer radically different pictures.
Like different philosophical takes.
Kind of, but they have physical implications too. Each tries to solve the measurement problem, but often at a certain cost, asking us to accept something strange about reality, which is why there's no single consensus view.
Okay, what are the main ones?
Well, the oldest sort of default view is the Copenhagen interpretation. Think Bohr, Heisenberg.
The founders.
Right. It's very pragmatic. It basically says, don't worry about what the electron is before you measure it. Physics is only about predicting measurement outcomes.
So the wave function isn't real.
In this view, it's just a mathematical tool for calculating probabilities. Wave and particle aspects are complementary, mutually exclusive ways reality can appear to us. You can measure one or the other, never both at once. The cost here is giving up on an objective reality independent of observation. It kind of leads to the shut up and calculate approach.
Okay, pragmatic, but maybe unsatisfying. What else?
Then you have the de Broglie-Bohm theory, or pilot wave theory. This one does believe in an objective reality.
How does it work?
It says there's always a real particle with a definite position, even when we're not looking. But there's also a real wave, the wave function, that acts like a pilot wave, physically guiding the particle's trajectory.
So in the double-slit.
The particle definitely goes through one slit, but the pilot wave goes through both, creating the interference pattern and guiding the particle to land in the bright spots. The apparent randomness. That's just because we don't know the particle's exact starting position.
That sounds more intuitive. What's the cost?
The cost is non-locality. The pilot wave has to exert influences instantaneously across space, which seems to clash with Einstein's relativity, where nothing travels faster than light. It's a tricky point.
Okay. Non-locality, what's the third main one?
The most extravagant one, perhaps, the many worlds interpretation, MWI.
Many worlds. Yeah. Sounds like science fiction.
It kind of does. MWI takes the wave function completely seriously as real and gets rid of wave function collapse entirely.
No collapse. So how do you get a single outcome?
You don't. According to MWI, every time a quantum measurement could happen with multiple outcomes, the entire universe branches. It splits into parallel universes, one for each possible outcome.
Seriously?
Seriously. So in the double slit, when the electron hits the screen, the universe splits. In one universe, it landed here. In another parallel universe, it landed there. And there's a version of you in each branch who saw that specific outcome.
Whoa. So there are infinite parallel universes constantly splitting off.
That's the implication. The cost is obviously this enormous unobservable multiverse. But mathematically, it's quite elegant because it just follows the Schrödinger equation without adding collapse.
Mind blown. Okay, Copenhagen, pilot wave, many worlds. Are there any actual physical processes involved here, or is it all just interpretation?
There is a very important physical process called quantum decoherence. It's relevant to all interpretations and helps explain why we don't see quantum weirdness on our scale.
Decoherence, what's that?
It's basically how a quantum system interacts with its environment. Air, molecules, photons, whatever. These interactions rapidly scramble the delicate phase relationships needed for superposition.
Like the environment measures the system constantly.
Exactly. A macroscopic object like a cat or a billiard ball is constantly interacting with billions of particles. This environmental measurement destroys its quantum coherence almost instantly, making it look like it's in one definite state.
So decoherence explains why my coffee cup isn't in two places at once.
Pretty much. It explains the appearance of collapse for large systems.
Yeah.
But it doesn't fully solve the measurement problem on its own.
Why not?
Because even after decoherence, in principle, the system and environment together are still in a giant superposition, just one that looks classical to us. It doesn't explain why we experience only one specific outcome out of all the possibilities decoherence leaves open. It pushes the problem up a level, you could say.
Okay. Wow. So these interpretations give different pictures, but maybe the fundamental issue is with the concepts of particle and wave themselves. Is there a deeper framework that gets beyond this duality?
Absolutely. And that brings us to the modern synthesis, quantum field theory, or QFT.
QFT, I've heard of it. It combines quantum mechanics and relativity.
Special relativity, yes. And it fundamentally changes the game. It dissolves the wave-particle duality paradox by introducing a completely new, more fundamental picture of reality.
Okay, this sounds important. What's the core idea of QFT?
The central idea is radical. It says the most fundamental building blocks of the universe are not discrete particles.
Not particles. Then what?
Fields. Continuous fluid-like entities that permeate all of space-time. Think of them like invisible, underlying stuff everywhere.
Fields like magnetic fields.
Sort of, but more fundamental. QFT says there's a field for every type of fundamental particle we know. There's an electron field, a photon field, which is the electromagnetic field, quark fields, a Higgs field. Everything arises from these fields.
So if the fields are fundamental, what happens to particles? Are electrons and photons not real anymore?
They are real, but they get demoted. In QFT, a particle is no longer the basic thing. It's understood as a quantized excitation of its underlying field.
A quantized excitation, like a ripple.
Exactly like a ripple, or maybe a localized vibration, or a discrete bundle of energy within the field. Imagine the field as a calm ocean. A particle is like a wave crest, a localized disturbance that travels across it.
So particles are just happenings on the field.
Precisely. They're temporary localized manifestations of the field's energy. The fields are the persistent reality. The particles are events occurring within those fields.
Okay, that's a big shift. How does thinking in terms of fields solve the wave-particle duality puzzle?
It handles it beautifully, almost naturally. Both behaviors emerge from the field itself.
Wow.
Well, the wave-like behavior, that comes directly from the field nature. Fields are inherently spread out, they can overlap, interfere, diffract, all the things waves do. The wave in the double-slit experiment. That's simply the electron's field spreading out and passing through both slits.
Okay, the field itself is wave-like. Then where does the particle part come from, the dots on the screen?
That comes from the quantization part of quantum field theory. Quantum mechanics dictates that energy in these fields can only be added or removed in discrete chunks, quanta.
The ripples have to be certain sizes.
Exactly. So when a field, like the electron field, interacts with something, like a detector screen, it has to exchange energy in one of these discrete packets. That localized exchange, that quantum hit, is what we detect as a particle, a dot.
So it's not that an electron is a wave or is a particle. It's an excitation of a field that propagates like a wave but interacts like a particle.
You've got it. There's no contradiction within the entity itself. The duality arises from how this underlying field behaves under different circumstances, propagation versus interaction. The field is the fundamental thing, manifesting differently.
Does QFT explain anything else that was puzzling?
Oh, lots. Particle creation and annihilation, like that pair production we mentioned, that's just adding or removing excitations, ripples, from the field. It requires energy, of course, via EMC.
Makes sense.
It also explains why all electrons, everywhere in the universe, are perfectly identical.
Wow.
Because they aren't separate little things. They're all just excitations of the same single universal electron field. Every electron is just another ripple in the same underlying ocean.
That's elegant. So QFT provides this unified picture where the paradox just dissolves.
Exactly. The paradox was a result of trying to force classical concepts, tiny balls or spread out waves, onto a quantum reality that's fundamentally different. QFT gives us the more accurate, albeit abstract, description, quantum fields.
Okay, so let's circle back to where we started. We asked if the idea everything is just a wave holds true. Based on this deep dive, what's the final verdict?
Well, that initial idea, often rooted in a misunderstanding of Einstein leading to waves, is a noble attempt at unity, but it's not quite right.
Needs refinement.
Definitely. Einstein tells us mass is rest energy, super important, but it's not about the form or behavior wave or particle in the quantum sense. That behavior, the wave-like part, comes from de Broglie, linked to momentum.
And the idea of a classical particle as a tiny solid ball, that is pretty much gone.
Oh yeah, that concept is definitely redundant in fundamental physics. But, and this is key, simply replacing it with the classical idea of a wave isn't accurate either. That's also inadequate.
So neither classical picture fits perfectly.
Right. The modern answer from QFT is more subtle. It's not really correct to say everything is a wave. It's much more accurate, though maybe less intuitive, to say that everything is an excitation of a quantized field.
Excitation of a quantized field, that's the takeaway.
That's the core concept from our best current understanding.
So those old ideas, particle and wave, they aren't totally thrown out, but they're demoted, like useful labels for certain aspects.
Precisely. They survive as context-dependent approximations. Particle is what we call the discrete, localized, quantized way the field interacts or is detected. Wave describes the continuous, probabilistic, spread-out way the field evolves and propagates, leading to interference.
They're descriptions of how we experience the field's behavior.
Exactly. Useful descriptions for different situations, but the underlying reality is the field itself.
Okay, so the final provocative thought then, what does this actually mean for, well, for us, for you listening? If everything you see and touch, everything solid, is ultimately just a complex pattern of excitations, ripples, and these invisible quantum fields.
Yeah, what does that imply about the nature of solidity,
Yeah.
of existence itself? Is that chair you're sitting on truly solid? Or is it just a very stable, persistent pattern of field excitations interacting in a way that resists your own field excitations?
A truly mind-bending place to end up. We hope this deep dive gave you a clearer picture of this fundamental question, maybe cut through some confusion, and perhaps sparked even more curiosity about the utterly strange and fascinating reality we're all part of.